Welcome to the ENME 351 video lecture series. This is part one of a three-part installment in which we'll be exploring analog to digital conversion. This lesson focuses on discrete time and amplitude signals. An analog signal, such as a voltage from a sensor, is continuous in both time and amplitude. The microcontroller on the Arduino, however, can only process digital signals. So we need an analog to digital converter, or an ADC, sometimes abbreviated AD. And ADCs are available as a peripheral on the microcontroller on our Arduino, and this will permit us to go from this analog world to the digital world. Now, digital microcontrollers can only approximate these analog signals. And here we explore the primary two components of this approximation, discrete time and discrete values. Let's begin with discrete time. As you're aware, microcontrollers execute instructions in discrete intervals, and these intervals are based on the system clock. For the Arduino Uno, for example, this is a 16 megahertz clock. So, for example, I might have an analog read buried inside a loop function, where the blue dots here represent the measurement each time through the loop. So these blue dots are what we refer to as the sampled signal. Some key definitions to discuss at this point include the time interval between samples. We call this delta t. And a reminder here, we're sampling at a constant rate. So delta t is going to be my sampling time. Now the inverse of delta t, or 1 over delta t, that will describe my sampling frequency, fs. Let's define then a sampling time on the Arduino. Here we have an analog read statement inside of a loop function, and this will be followed by a delay. And here my delay is set to 500 milliseconds or half a second. Let's say the blue dots on my figure represent measurements taken every 500 milliseconds. As a result, my delta t will be 1/2 of a second. And I could change the delay, let's say to 1500 milliseconds, and in this case, delta t would be 1.5 seconds, and the voltage readings on my analog input pin on my Arduino might be represented now by these green dots. So we see then there are consequences from sampling at slower rates in terms of trying to evaluate the true signal. Microcontrollers are also limited in how they represent numbers. An analog or continuous signal, in essence, has an infinite number of decimal places which I can use to describe the signal. A microcontroller, however, is limited to discrete representations of a signal. I can represent these discrete values, let's say, with these horizontal lines. My digital signal, then, will be limited to these values, and it might look something like this. And this signal is referred to as the quantized signal. We think of this as quanta, or discrete values, which my digital signal can take. I can also define a quantization error at some point in time, and this error will be equal to the ideal or analog value minus the quantized or digital value. So it is evident that I am left with a rather crude approximation of my analog signal, and this level of crudeness is dependent on how many different values my digital signal can take. And the quantization error is directly dependent on the resolution or number of bits of my ADC. And finally, we have the true approximation of an analog signal by the ADC on my microcontroller. This digitized signal is discrete in both time, vertical lines, and amplitude, horizontal lines. My digital signal may exist only at the intersection of these lines. So my signal might look something like this, where each dark blue circle now represents the sampled N quantized signal. And we see that each component of the digitized signal has its own quantization error. This representation tells us that we can obtain a better approximation of the analog signal by either increasing the sampling frequency, which will increase the density of vertical bars here. This effectively reduces the time between samples, reduces our delta t, and increasing the ADC resolution. So again, increasing the density now of the horizontal bars. Ideally, we would increase both, but performing one or the other will give us an improved approximation of the analog signal.